Okay, so we are now moving into the exceptions to the octet rule. The octet rule being structures that follow the rules of needing 8 electrons in their outer shell. And there are a number of exceptions to that rule. Okay, so 3 types of ions or molecules that don't follow the octet rule. One, you have ions or molecules that have odd number of electrons. We'll take a look at those. Then you might have ions or molecules that require less than an octet to be stable or to be correct. And then the last type would be ones that go beyond 8 valence electrons, so having 10 or 12 electrons around the atom. So let's just step into that now. Okay, odd number ones. So you've got these, this example of nitrogen monoxide. So a fairly rare, or this type of situation where you have an odd number of electrons is a pretty, it doesn't happen too often, tends to be pretty unstable, pretty reactive compound, so it reacts and basically fixes the issue that it has an odd number of electrons pretty quickly. But it can happen, and so therefore just kind of figuring out how to develop the electron structure for that. Another type, or the other way that it might break the rules, is having a central atom that actually has fewer than 8 electrons. So here our example is, so you've got boron trifluoride, and when doing the Lewis dot structure and making sure everything has a full octet, you end up getting, and this would have a 3 resonance structure if this was the correct structure. But you notice how the formal charges are really off, because the idea that boron, being the lower electronegative number, carries the negative formal charge, and the fluorines, which are the most electronegative out of any element, would carry a 0 or a +1, while the central atom is -1, just really doesn't fly very well. And so when you look at it, so kind of a description down here, giving boron a filled octet places a negative charge on the boron and positive charge on the fluorine, and this just isn't an accurate picture. What actually happens is boron just is fine with 6 valence electrons, so just 3 single bonds rather than maintaining the octet, but really throwing off formal charges and kind of mess it up. And so boron is actually really copacetic, just having 3 bonds, no lone pairs, or no additional electrons around it. And then all the fluorines also will have formal charges of 0. So it works quite well when you do it that way. So if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, then we don't fill the octet. It just kind of, it's less stable that way versus having a central atom that has fewer electrons around it. Okay, the last type of exception are ones that have more than 8 electrons around them. And this is something that I alluded to earlier this week, and it really is only possible for atoms that are in the 3rd energy level or higher, because there's a d orbital where hybridization can occur, where you can have electrons occur, and that's kind of what this is saying here. It's allowed to expand the octet of atoms on the 3rd row or below, presumably because the d orbitals in these atoms participate in the bonding relationship rather than only the p and the s involved in the bonding. So even though we can draw a Lewis structure for the phosphate ion that has only 8 electrons, so this is a different, so the phosphate ion, PO4 3-, so we can do this. The better structure puts a double bond between the phosphorus and one of the oxygens. So this one you wouldn't necessarily expect automatically, but it tends to be the structure on the right rather than the left, and that's kind of how it ends up being. This eliminates the charge on the phosphorus and the charge on one of the oxygens, so it becomes a bit more stable, less formal charge necessary. So, the lesson of the more than 8 exception is when the central atom is on the third row or below, and expanding in its octet eliminates some formal charges, then we should do it when making the structure. And that's it for today. And if you like this video, make sure to subscribe, and we'll talk to you tomorrow. See you tomorrow.